A quick refresher on model building. Hands-on machine learning with scikit-learn, Keras, and TensorFlow by Aurélien Giron. Previously, we started building machine learning models. These tools learn from data to make predictions. We feed our model input features and target values. The model learns relationships to make predictions. Imagine predicting house prices. We provide features like size, bedrooms, and location. The model predicts the sale price of a new house. This is the essence of machine learning. Next, we'll explore hyperparameter tuning and cross-validation. Diving deeper, understanding hyperparameters. As we've seen, building a machine learning model involves feeding it data and letting it learn the underlying patterns. But there's more to the story. Behind the scenes, these models have knobs and dials that control their learning process. These knobs and dials are known as hyperparameters. Think of hyperparameters as settings that influence how a model learns. For instance, imagine training a model to recognize handwritten digits. One crucial hyperparameter might be the learning rate. This parameter determines how quickly the model adjusts its internal parameters based on the data it sees. A high learning rate means the model makes rapid adjustments, which can be beneficial if the optimal settings are far from the initial guess. However, it can also lead to overshooting the optimal settings. Conversely, a low learning rate results in slower adjustments, potentially getting stuck in suboptimal settings. Finding the right balance for these hyperparameters is key to building a well-performing model. The power of grid search for optimal hyperparameters. Now that we understand the significance of hyperparameters, how do we determine the optimal values for our model? This is where GridSearchCV comes to the rescue. GridSearchCV is a powerful technique that automates the process of finding the best hyperparameter combination. Imagine you have a set of potential values for each hyperparameter you want to tune. GridSearchCV systematically tries all possible combinations of these values. For each combination, it trains the model, evaluates its performance using cross-validation, which we'll discuss in the next section, and records the results. Let's consider a simple example in Python using scikit-learn Python from sklearn.model-selection import, GridSearchCV from sklearn, ensemble import, random forest classifier, param_grid =rf random forest classifier, grid_search GridSearchCV estimator rf param_grid param_grid cv 5 grid search fit x_train y_train print best parameters grid. In this example, we're tuning a random forest classifier, defines the hyperparameters and their potential values, then explores all combinations, finding the best performing one based on 5-fold cross-validation. Cross-validation, ensuring your model's reliability. How do we ensure our model's performance generalizes well to unseen data? This is where cross-validation plays a crucial role. Imagine training a model on a single dataset and evaluating its performance on the same data. The model might achieve high accuracy, but this doesn't guarantee it will perform well on new unseen data. This phenomenon is known as overfitting. Cross-validation addresses this issue by splitting the data into multiple folds. The model is then trained on a subset of the folds and evaluated on the remaining fold. This process is repeated multiple times, providing a robust estimate of the model's performance on unseen data. Decision trees, a visual approach to machine learning. Now let's shift our focus to a specific type of machine learning algorithm, decision trees. Decision trees are powerful and intuitive models that make predictions by mimicking human decision-making processes. Imagine you want to predict whether a customer will click on an online ad. A decision tree might start by asking, is the customer interested in technology? If the answer is yes, it might further inquire, has the customer visited technology websites recently? Based on the answers to these questions, the tree would navigate through a series of decisions, ultimately leading to a prediction of whether the customer is likely to click on the ad. This tree-like structure, with its branches representing decisions and its leaves representing predictions, makes decision trees easy to visualize and interpret. This transparency is a key advantage, especially when understanding the reasoning behind a model's predictions is crucial. Classifying with decision trees, a practical example. Let's dive into a practical example of using decision trees for classification. Imagine we have a data set of iris flowers, each described by its sepal length, sepal width, petal length, and petal width. Our goal is to build a decision tree that can classify iris flowers into their respective species, setosa, versicolor, virginica, based on these features. Here's how we can achieve this in Python using scikit-learn from sklearn datasets import load _iris from sklearn.tree import DecisionTreeClassifier from sklearn model selection import train _test _split x _train x _test y _train y _test equals sign train test split x y test _size equals sign 0. 2. This code snippet loads the iris dataset, splits it into training and testing sets, creates a decision tree classifier, trains the classifier, and finally, uses the trained model to make predictions on the test data. Decision trees for regression, predicting continuous values. While we've focused on classification, decision trees are equally adept at regression tasks, where the goal is to predict a continuous value rather than a discrete class label. Imagine predicting house prices. A decision tree might start by asking, is the house located in a desirable neighborhood? If yes, it might further inquire, what is the house's size? Based on the answers to these questions, the tree would navigate through a series of decisions, ultimately arriving at a predicted house price. The key difference in regression is that instead of predicting a class label at each leaf node, the tree predicts a continuous value. This value is typically the average of the target values of the training instances that end up in that leaf node. The process of building and using decision trees for regression in Python is very similar to classification, with the primary difference being the choice of the model. Instead of, we would use from scikit-learn. Visualizing decision trees for enhanced understanding. One of the most significant advantages of decision trees is their interpretability. Unlike many other machine learning models that appear as black boxes, decision trees can be easily visualized, allowing us to understand the reasoning behind their predictions. Scikit-learn provides convenient tools for visualizing decision trees. Here's an example. Python from sklearn, tree import plot, _tree import matplotlib.pyplot as pltplot.figure fig size 12.8, plot _tree, tree _self, feature _names equals sign iris, feature _names, class _names equals sign iris, target _names, build equals sign true, pollet.show. This code snippet generates a visual representation of the trained decision tree, showing the decision nodes, branches, and leaf nodes. The end parameters provide labels for better interpretability. Visualizing decision trees allows us to gain insights into the model's decision-making process, identify the most influential features, and potentially improve the model by adjusting its hyperparameters or engineering new features. Advantages and disadvantages of decision trees. Decision trees offer several advantages for machine learning tasks. Interpretability. They are easy to understand and interpret. Their structure shows the decision-making process. Versatility. They handle both classification and regression tasks. However, they have limitations. Overfitting. They can be prone to overfitting. Instability. Small data changes can lead to different trees. Wrapping up and looking ahead ensemble methods. In this essay, we've delved into the world of advanced machine learning techniques. We explored the crucial concepts of hyperparameter tuning and cross-validation, essential for building robust and reliable models. We then ventured into the realm of decision trees, powerful and interpretable models that mimic human decision-making processes. We learned how to build, train, and visualize decision trees for both classification and regression tasks, using practical examples to solidify our understanding. We also discussed the advantages and disadvantages of decision trees, highlighting their interpretability and versatility, while acknowledging their potential for overfitting and instability. As we move forward in our machine learning journey, we'll explore even more sophisticated techniques. Our next stop will be the exciting world of ensemble methods, where we'll discover how to combine multiple models to achieve even higher accuracy and robustness. Conclusion. Mastering machine learning is an ongoing journey of exploration and discovery. By understanding the fundamental concepts of hyperparameter tuning, cross-validation, and decision trees, we've equipped ourselves with powerful tools to tackle a wide range of real-world problems. As we continue to explore the vast landscape of machine learning, Let's embrace the challenges and celebrate the triumphs, always striving to build models that are not only accurate but also interpretable, reliable, and ultimately beneficial to society.